What's up everyone, it's Stack Lessons here. Welcome back to the channel. Today we're diving into Amazon Redshift, distribution, sort keys, and the warehouse deep dive. Let's get into it. By the end of this video, you'll know exactly why one Redshift query takes 5 seconds and an identical-looking query takes 5 minutes. And Redshift is one of the most heavily tested services on the Amazon Web Services Certified Data Engineer Associate exam. We're going deep on the internals, distribution styles, sort keys, the copy command, Spectrum, streaming materialized views, data sharing, and serverless, because the exam doesn't just ask what Redshift does, it asks how it does it. Here's the thing nobody tells you about Redshift. 2 queries can look identical, hit the same table, return the same rows, and one runs in 5 seconds while the other takes 5 minutes. The difference is almost never the structured query language itself. It's where the data physically lives on disk and which compute slices have to talk to each other to answer your query. That's the entire game, and it's what this video is about. Redshift is one of the big 5 services on the exam, and the questions go deep. They test internals, how data is distributed across nodes, how it's sorted on disk, how it's loaded, and how queries actually execute. Knowing that Redshift is a data warehouse won't get you points. You need to know how it works under the hood. The copy command is the fastest bulk load path. Spectrum extends queries directly into S3. Serverless removes cluster management entirely. And data sharing lets multiple teams query the same data without copying it. But everything else sits on top of one foundation. 2 knobs decide most performance outcomes, and those 2 knobs are distribution style and sort key. Get those right, and the rest of the service falls into place. Quick refresher on the physical layout because everything else depends on it. At the top sits the leader node, which plans queries but stores no user data. Underneath, you have compute nodes, which actually hold and process the data. And here's the part most people miss. Each compute node is divided into slices, which are independent storage and CPU units. A node with 8 slices is really 8 little workers running in parallel. Every row in your table lives on exactly 1 slice, and the distribution style is what decides which slice gets which row. That choice is the foundation of everything that follows. You get 4 choices for distribution style: key, even, all, and auto. Pick the right one, and joins happen locally on each node with 0 network traffic. Pick the wrong one, and every join triggers a massive shuffle, where Redshift redistributes billions of rows across the cluster just to line up matching keys. That's the difference between a fast warehouse and a slow one, and the exam tests this constantly. Picture a warehouse with 8 forklift drivers, where each driver is 1 slice. Key distribution says all boxes labeled customer 123 go to driver 3 every time. Same key, same slice, predictable placement. Even distribution deals boxes out like playing cards, 1 to each driver in a round robin regardless of what's in the box. All distribution gives every driver their own copy of the small price sheet, so nobody has to walk across the warehouse to look up a price. Auto is different. The warehouse manager watches how the inventory grows and switches strategies over time, starting with one approach and adapting as the table changes. That covers all 4 distribution styles, and you'll pick between them based on the size and access pattern of each table. Here's why DEA-C01 matters so much. Both the order's fact table and the customer's dimension are distributed on customer_ID Redshift hashes that column, so a row with customer 1 always lands on slice 1, and the matching customer record also lands on slice 1. Same for customer 2 on slice 2 and customer 3 on slice 3. When you join orders to customers, every slice has the matching rows it needs, sitting right there locally. 0 network shuffle, joins run in parallel across all slices, and the query finishes in a fraction of the time. This pattern is called a collocated join, and it's the single biggest performance lever in Redshift. On the left, the rules of thumb. Use key when two large tables join on a high cardinality column. Use all for small dimensions under about 3 million rows that rarely change your date dimension, your country lookup. Use even when a table never joins or there's no clear key. And use auto when the question gives you no clear pattern, because that's the Amazon Web Services recommended default. On the right, the traps. Never put key on a low cardinality column like gender or country. Every row with the same value hashes to the same slice, and one node ends up holding 80% of the data. Never put all on a 50 million row table. Your storage multiplies by the node count. And never pick key on a column no actual query joins on. The entire purpose of DISTKEY is collocation, so a key no join uses gives you skew with no upside. Finally, avoid even for fact tables that always join, because Redshift will redistribute the data on every single query. Let's make this concrete with a Nexer retail example. You've got a billion row orders fact table that joins to a customer dimension on customer_ID and to a tiny 200 row date dimension on date_key. The right answer fact table gets DISTKEY on customer_ID. Customer dimension also gets DISTKEY on customer_ID. And the date dimension gets DISTSTYLE, all because 200 rows replicated to every node costs you almost nothing. Result: both joins happen with zero network shuffle. This exact pattern shows up on the exam almost word for word. Straight from the Redshift developer guide. All distribution multiplies your storage by the number of nodes. Replicate a table to a 10-node cluster, you're storing it 10 times. So loads, updates, and inserts all get slower because Redshift has to write the same rows to every node. The official guidance is that all is appropriate only for relatively slow-moving tables. Translation: small dimensions that change rarely. If the table is being constantly updated, all is the wrong choice. Now let's talk about sort keys, which are the second big knob. Redshift stores data in immutable 1 megabyte columnar blocks, and every block carries a tiny piece of metadata called a zone map, basically the minimum and maximum value of each column in that block. When your query says where sale_date is between January and March, Redshift looks at the zone maps and skips entire blocks where the date range doesn't match. Sort keys decide how rows are physically ordered on disk, which decides how effective that block skipping is. A good sort key can turn a full table scan into reading 2% of the blocks. On the left, compound sort keys the default. Redshift sorts by the first column, breaks ties with the second, and so on, like a phone book. Perfect when queries filter on a known prefix like sale date then region. Cheap to maintain, and you'll use it about 90% of the time. On the right, interleaved sort keys give equal weight to every column using a z-order curve. The catch: vacuum REINDEX is brutally expensive because Redshift rewrites nearly every block. Max 8 columns, a hard cap, and it's a niche choice. Only worth it for tables that load infrequently but get queried on totally different column combinations each time. Read the query pattern in the question, and the sort key picks itself. A sales fact table where virtually every query filters by date range first, that's a compound SORTKEY on sale date with region as the second column. An analyst exploration table where filters change every day across 4 different columns, that's the rare case for an interleaved SORTKEY. And when the question offers no clear filtering pattern, auto is the safe answer. Redshift picks for you and adapts as the table grows. But watch out for one trap. A table loaded every 5 minutes from a streaming pipeline, never interleaved because the vacuum REINDEX cost will eat you alive. The pattern is simple. Read the filter clause first, then map it to the sort strategy. Quick rule that the exam loves: never use insert statements to bulk load Redshift. Inserts route through the leader node, which becomes a bottleneck, and they load one row at a time. The copy command is the right answer. It pulls data in parallel from S3, DynamoDB, or EMR, with every slice on every compute node loading its own files at the same time. We're talking orders of magnitude faster, not just a little faster. Here's the picture. You've got 6 files sitting in S3 on the left and a Redshift cluster with 5 slices on the right. A single copy command splits the work across all 5 slices, and each slice pulls its assigned files in parallel. More files than slices? Even better, slices grab the next file as soon as they finish their current one. The key insight is that file count and size matter. A best practice is to have at least as many files as you have slices, so every slice stays busy. One giant file is the worst case, because only one slice can read it. This one's straight from the developer guide, and it shows up on the exam regularly. If you fire off multiple concurrent copy commands into the same table, Redshift is forced to serialize them. They don't run in parallel, they run one after another slowly, and then you have to vacuum at the end. The right pattern is always one copy command pointing at many files, not many copies pointing at one file each. If you see an answer choice that says, run multiple copy operations in parallel, that is the wrong answer. A manifest file is just a small JSON document listing the exact S3 objects to load. Each entry has a URL and an optional mandatory flag. When mandatory is true, copy fails loudly if any file in the list is missing. No silent partial loads, no surprises. You then point copy at the manifest file instead of an S3 prefix, and add the manifest keyword on its own line before format as Parquet. Notice we're loading 3 specific Parquet files for the March 15th Nexer retail orders batch. Tomorrow's manifest will list tomorrow's files. Each load is exact, deterministic, and idempotent. Why bother with manifests instead of just pointing copy at an S3 prefix? 3 reasons. First, prefix loading grabs whatever files happen to be sitting in that prefix at load time, which is risky if stray files are present, or if a partially written file from an upstream job got left behind. The manifest specifies the exact files that must be loaded for the run to count. Second, setting mandatory :true makes copy fail loudly if any file is missing, so you never get a silent partial load that quietly corrupts your data. Third, manifests are idempotent and deterministic by design. Rerun the same manifest and you load the same data every time. That's exactly the property you want for production pipelines, where reruns after a failure should never duplicate or skip records. Unload is the mirror image of copy. You give it a select query and an S3 destination, and every slice writes its results in parallel. The pattern shown here is the standard archive pattern: pull old Nexer retail orders out of the warehouse, write them to S3 as Parquet, partitioned by year and month. Why Parquet? Amazon Web Services' own benchmarks show Parquet unload is up to 2 times faster than CSV and produces files up to 6 times smaller. And once those files are in S3 with that partition layout, they're ready for Spectrum or Athena to query as external tables, which is exactly where we're going next. Redshift Spectrum is what makes Redshift a lakehouse. Here's how it flows. The Redshift R3 cluster on the left holds your hot data, say, the last 90 days of Nexer retail orders. You define an external schema in Redshift that points at the glue data catalog in the middle, which holds the table metadata for files sitting in S3. When your query touches an external table, Redshift dispatches the work to a separate Spectrum compute layer on the right, which reads the Parquet files directly from S3. The result comes back to your cluster and joins with your hot internal tables. One SQL query, two storage tiers, no data copied between them. And here's the trap the exam loves. Spectrum cannot read Glacier Flexible Retrieval, and it cannot read Glacier Deep Archive. Period. Think of Spectrum as a librarian with keys to the open access reading rooms. Glacier Flexible Retrieval is the off-site warehouse. The librarian can't even see those books until you formally request them and a truck brings them back hours or days later. So if you see a question about Spectrum querying archived data, look carefully at the storage class. If it says Glacier Flexible Retrieval or Deep Archive, you must restore those objects to S3 standard first, typically with S3 batch operations, before any Spectrum query will work. Memorize this list. On the left, the storage class's Spectrum can read directly S3 standard, standard infrequent access, one zone infrequent access, intelligent tiering, and notably Glacier instant retrieval. That last one trips people up because Glacier is in the name, but instant retrieval really is instant. Spectrum reads it like standard. On the right, the two it cannot read, Glacier Flexible Retrieval and Glacier Deep Archive. The fix, restore to standard first. For bulk jobs, use S3 batch operations to bulk restore, or design a lambda to restore before query, triggering the restore the moment a partition is about to be touched. Pick the pattern that matches your access cadence. This is the modern streaming ingestion pattern, and it's beautiful in its simplicity. Step 1. Create an external schema that points at your Kinesis data stream with an IAM role that has Kinesis read permissions. Step 2. Create a materialized view with auto refresh yes, selecting from that external schema. That's it. Next, your retail transactions flow from Kinesis directly into Redshift with no S3 staging area, no fire hose, no glue job in the middle. The materialized view refreshes incrementally, typically every minute, and you query it with regular SQL. From event to query result in under a minute with maybe 10 lines of code. 3 gotchas that bite teams in production, plus one big payoff. First, one materialized view per Kinesis stream. Don't try to union multiple streams together in a single view because auto refresh will fail. Second, the IAM role needs 5 actions on the stream resource. Describe stream summary, get shard iterator, get records, and list shards. It also needs list streams on all resources. Miss any of those and the refresh silently fails. Third, auto refresh is opportunistic. Redshift refreshes the view as soon as possible after new stream data arrives, but the timing depends on cluster load. If you need deterministic timing, use the Redshift scheduler to explicitly schedule refresh materialized view. And here's the payoff. This pattern is the lowest latency way to land Kinesis data into Redshift, with no S3 staging and no fire hose in the middle. That's a meaningful gap compared to the fire hose into S3 then copy route, which adds minutes of buffering before the data is queryable. Data sharing solves a real organizational problem. The producer cluster at the top runs the heavy ETL jobs and pays for the storage. 3 different consumer clusters underneath. The BI team running Tableau dashboards, data science doing ad hoc analysis, and finance running on a serverless workgroup. Each query the same current data read-only with 0 copying. Each consumer pays only for their own compute. Think of it like a Netflix account with profile sharing. The account holder pays for the movies, every viewer gets their own profile, and everyone watches the same library at the same time. The key requirements, both producer and consumer must be on R3 nodes or serverless, and within the same account, encryption types must match on both sides. That means both encrypted or both unencrypted, you can't mix. For cross-account or cross-region sharing, encryption is mandatory on both sides. Burn this into memory. Data sharing requires R3 cluster types or Redshift serverless on both sides. That's it. Older node types like DC2 and DS2 cannot participate. neither as producer nor as consumer. If the exam shows you a scenario where someone wants to share data from a DC2 cluster, the right answer is migrate to R3 first. Then add the encryption requirement on top, and you've got the full picture. Memorize this trigger phrase. When you see least operational overhead in a Redshift question, especially combined with words like intermittent, unpredictable, or sporadic, the answer is almost always Redshift serverless. There's nothing to provision, nothing to size, no maintenance windows to schedule. Amazon Web Services handles all of it. You just submit queries, and you pay only when something is actually running. On the left, provisioned RA3. You pick node types, you pick the count, you configure scaling, and you pay around the clock whether you're querying or not. That's the right choice when your load is steady and predictable and you want maximum control. It's like leasing an office building. On the right, serverless. No clusters to size, no scaling policy to set. You pay per RPU second and only when queries are actually running. That's the right choice for intermittent or unpredictable workloads, like a co-working space where you only pay when someone shows up to work. Quick mental model for vacuum. Redshift stores data in immutable 1 megabyte blocks. Once a block is written, it never changes. So when you delete a row, Redshift doesn't actually erase it. It just marks the row as a tombstone. Picture a notebook where you can only add pages, you cross out deleted lines with pencil, and eventually you photocopy only the live lines into a fresh book. That cleanup is vacuum. Update works the same way. Internally, it's a delete plus an insert, which means heavy update workloads silently bloat your tables. The good news is Auto Vacuum handles vacuum delete in the background, so you rarely run it manually. You only reach for manual vacuum sort or vacuum REINDEX after big loads or after changing an interleaved sort key. Concurrency scaling is Redshift's auto scale-out for burst red traffic. When your workload management queue starts backing up, Redshift spins up a transient cluster, routes the queued queries there, and shuts it down when the burst passes. The credit math is worth memorizing. Each cluster earns about 2.5 minutes of free credit per hour of operation, capped at 1 hour per day. Amazon Web Services claims that's enough for 97% of customers. Now, 2 important traps. Concurrency scaling only helps queued queries, not slow queries. A single slow query stays slow no matter how many extra clusters you have. Write scaling for copy operations requires R3 nodes specifically. Read scaling is supported on DC2, R3, and serverless, but check the current docs for your node type, as the support matrix changes over time as Amazon Web Services adds and retires node families. Amazon Web Services own number, 97% of customers never pay a dime for concurrency scaling, because their burst patterns fit inside the free 1 hour per day credit bucket. That's why on the exam, when you see burst of read queries during business hours, the answer is just enable concurrency scaling on the workload management queue. Cost is essentially 0 for typical patterns. 5 mistakes that cost real exam points with their fixes. On the left, common wrong choices. DISTKEY on a low cardinality column like gender causes severe skew. Interleaved sort on a frequently loaded table. Vacuum REINDEX kills you. Many concurrent copies into one table. Redshift serializes them. Spectrum query over Glacier Flexible Retrieval. Silent failure. Provisioned cluster for an intermittent dev workload, paying around the clock for nothing. On the right, the correct patterns. DISTKEY on a high cardinality join column. Compound sort with date as the first column. Single copy with a manifest and mandatory true. Restore from Glacier first or keep the partition in standard. And Redshift serverless for intermittent workloads. These 5 pairs cover most of the Redshift mistakes the exam tries to catch you on. Burn this cheat sheet into memory. Least operational overhead with analytics serverless. Cross-cluster sharing without copies, data sharing on RA3, both sides encrypted. Kinesis low latency, materialized view with auto refresh, yes. Query S3 directly from Redshift Spectrum with an external schema in the Glue catalog. Spectrum plus Glacier Flexible Retrieval, that's the trap. Restore to standard first. Date range filter always, compound sort key with date first. Exact files guaranteed, copy with a manifest and mandatory true. Burst of read queries, concurrency scaling on the workload management queue. That's 8 triggers, 8 answers. Match the trigger to the answer and you get the points. Question 1. A Nexer retail orders fact table has 2 billion rows and joins frequently to a 200-row date dimension and a 50 million row customer dimension on customer_ID. Which distribution strategy minimizes network shuffle? Is it A, orders DISTKEY on customer_ID, customer dimension DISTKEY on customer_ID, and date dimension DISTSTYLE all? B, orders DISTSTYLE even with both dimensions DISTSTYLE all? C, all 3 tables DISTSTYLE all? Or D, all 3 tables DISTSTYLE auto and let Redshift figure it out? Take a moment to think about it. The answer is A, DISTKEY on customer_ID for both orders and customers gives you a collocated join with 0 shuffle on that join. The 200-row date dimension is small enough that all costs almost nothing. You replicate 200 rows to every node. But all on the 50 million row customer dimension would explode your storage by the node count, which is exactly what option C and parts of option B get wrong. Question 2. An analytics team needs to query archived order data in S3 from Redshift. The data was lifecycled to S3 Glacier Flexible Retrieval to save cost. They run a Spectrum query and it fails. What's the correct fix? Is it A, recreate the external schema in the Glue data catalog? B, switch the cluster to RA3 nodes, Spectrum requires RA3 for Glacier. C, restore the objects from Glacier Flexible Retrieval back to S3 standard before querying. Or D, enable concurrency scaling so a transient cluster can read Glacier. Take a moment to think about it. The answer is C. Spectrum simply cannot read Glacier Flexible Retrieval or Glacier Deep Archive directly. There's no setting that enables it. You must restore the objects to S3 standard first, typically using S3 batch operations for bulk jobs. Worth remembering, Glacier Instant Retrieval is the only Glacier-class Spectrum can read natively, because despite the name it returns data instantly. Question 3. Nexer Retail wants to land Kinesis data streams events in Redshift with the lowest possible latency, with no S3 staging area. Which approach is correct? Is it A, use Kinesis data firehose to write Parquet to S3, then schedule a Glue job to copy into Redshift every 5 minutes? B, create an external schema from Kinesis, then a materialized view with auto refresh, yes. C, run a Lambda function that consumes from Kinesis and inserts each record into Redshift. Or D, use a WSDMS with Kinesis as the source endpoint and Redshift as the target. Take a moment to think about it. The answer is B, the streaming ingestion pattern with an external Kinesis schema and a materialized view set to auto refresh, yes, is the lowest latency, no staging path, typically under a minute end-to-end. Option A involves a firehose to S3 to copy pipeline that adds several minutes. Option C is an anti-pattern because inserts route through the leader node and won't keep up with stream throughput. Question 4. A finance team needs read-only access to the production sales data on the main Redshift cluster, but the data engineering team doesn't want copies and doesn't want finance queries impacting ETL performance. The main cluster runs on DC2. Large nodes. What's the correct architectural change? Is it A, set up nightly unload to S3 and have finance query via Spectrum? B, migrate the main cluster to R3 nodes and use data sharing to share data with a separate finance consumer cluster? C, enable concurrency scaling so finance queries run on transient clusters? Or D, create a red replica of the DC2. Large cluster for finance? Take a moment to think about it. The answer is B. Data sharing solves this exact problem: live, read-only access with no copying, and completely isolated compute per team. The catch is that data sharing requires R3 nodes or serverless on both sides, so the DC2 cluster must migrate first. Option C with concurrency scaling adds transient capacity to the same cluster, but it doesn't isolate workloads. Finance queries would still compete with ETL for resources. Question 5. A Redshift table is loaded every 10 minutes via copy and uses an interleaved sort key across 4 columns. Query performance has degraded significantly over the past few weeks. What is the most likely cause and best fix? Is it A, the DISTKEY is wrong, change it to even distribution? B, interleaved sort keys require expensive vacuum REINDEX as data grows, so switch to a compound sort key if queries filter on a leading column? C, the cluster is under-provisioned, enable concurrency scaling on the workload management queue? Or D, column compression is missing, run analyze compression and reload the table? Take a moment to think about it. The answer is B. Interleaved sort keys give equal weight to multiple columns, but they require vacuum REINDEX to maintain their structure, and that operation gets dramatically more expensive as the table grows. With frequent 10-minute loads, the sort structure degrades fast and reindexing can't keep up. If your queries typically filter on a single leading column, a compound sort key is far cheaper to maintain and usually faster in practice. Concurrency scaling doesn't help here because the problem is the data layout, not queue contention. 7 things to lock in. Distribution style decides which slice a row lives on key for big joins, all for small dimensions. Auto when the question doesn't tell you the access pattern. Compound sort key for predictable prefix filters. Interleaved only for true ad hoc multi-column queries on tables that don't load often. One copy with a manifest beats many concurrent copies every single time. Spectrum reads S3 in place, but not Glacier Flexible Retrieval and not Deep Archive, restore first. Materialized View with auto refresh yes is the Kinesis to Redshift path, no S3 staging needed. Data sharing requires R3 or serverless and encryption on both producer and consumer. And least operational overhead almost always means Redshift serverless. Lock those 7 in, and the Redshift questions become some of the easiest points on the entire exam. And that's a wrap on Amazon Redshift, distribution, sort keys, and the warehouse deep dive. If this helped you out, smash that like button and subscribe for more. See you in the next one.